Welcome everybody to this Licentiate Seminar by Viktor Döhlen, where he will present his licentiate thesis, Enhancing Hydropower with Energy Storage System, Merging Perspective on Inverter Design and Industrial Applications. With us we have some important persons. For the opponent we have Professor Massimo Bongiorno from Chalmers University in Gothenburg. Massimo received his master thesis in Palermo, Italy in 2002. After that, he's been in Gothenburg receiving his PhD in 2007. Now he's working as a full professor and head of division Electric Power Engineering. His interest is power electronics in power system, power dynamics and power quality. The respondent, Viktor Döhlen, received his master thesis from Lund University 2016. Spent 4 years at the Swedish Energy Agency before he started his industrial PhD at Sollefteå. There we have with us today Anders Bergman and Mikael Näsström here in the audience. The work has been conducted in the field of combining hydropower with electrical energy storage system to enhance functionality and reduce wear and tear of the power plants. I am Kent Bertilsson. I'm a professor in power electronics here at Mid-Sweden University. I have been the main supervisor for Viktor Döhlen during his work. Additionally, we have Sobi Barg here. He's been the co-supervisor. And we have Peng Cheng. He's been working also with involved in the practical work we have been conducting. So the procedure for this licentiate presentation is that first Viktor will present his thesis for approximately 30 to 40 minutes. The presentation is submitted is broadcasted in YouTube, and we have a Zoom meeting, and we are here physically located in Sundsvall. After the presentation, the YouTube stream will end, and we only continue here at the physically and in the Zoom meeting. After the presentation, we'll have a short technical break. And about 10 minutes after that, we'll have a discussion led by the opponent, between the opponent and the respondent. There's no technical time limit for it, but usually that lasts for about 1 hour. After the discussion, me and the examiner opponent will have a short meeting in a separate room. I will discuss the thesis, the presentation, and the So after that, we'll meet in. We will have the audience have the possibility to ask questions, and also on the Zoom meeting. And after that, we conclude this presentation, and we meet up for some coffee and in the S building. So I start with giving the word to Viktor to present his thesis, present his work. But first, you have the chance to mention if you have found some errors in the thesis.
Thank you. Yeah, I actually have found some errors that I'd like to point out before we begin. Let's see if I can get my right view here. Now it looks like everything is good. Yeah, so the errata page, I would like to point out that on page 14, it's incorrectly stated that the system should have no poles in the left-hand plane. They should, of course, be in the right-half plane. On page 62, it's stated that higher voltage and lower current decrease switching loss, but it should be conduction loss. I would also like to point out that in the appended paper 1, figure 3, the input to the current MPC algorithm should be the current set point, not the voltage set point, and that the output of the MPC algorithm selects a switching state directly, not through a PWM module as indicated by the schematic. On page 9 of paper 3, Makinen et al. Presented a system with decreased response time, not increased response time. I'm sure there are more, but these were the ones that I found. I think I will let it rip now. So I'm presenting my licentiate thesis, Enhancing Hydropower with Energy Storage, with the subtitle, Merging Perspectives on Converter Design and Industrial Application. So the content of my presentation will be that I'll give an introduction to the research project, Frequency Regulation 101, what is it, what's the use case? Then I'll go through the content of the thesis, what are the main parts of the thesis that we're discussing. And then the presentation will focus on summarizing and presenting some primary results from the appended papers in the thesis. I will begin with paper 3, as I think it's more intuitive that way, and then discuss paper 1 and paper 2 in that order. I will also present some additional results that are not yet published, but are part of the licentiate thesis. And then we'll go to conclusions and future work. So, as the title of the thesis reveal, the project focus is on the combination of hydropower and energy storage. I am an industrial PhD student employed at Sollefteå Forsen AB, which has been fully owned by Sollefteå municipality since 2016. The station is used as a case study and for experiments in the thesis work. And at Mid Sweden University, my home is with the Power Electronics Group. And at Mid Sweden, the work is focused on simulation and experiments on the power electronic systems needed to integrate the energy storage systems to the grid. So these are the two primary perspectives represented in this thesis. So the research project. The initial hypothesis of the project was that efficiently dimensioned energy storage systems may be combined with hydropower units to support each other's strengths. FFR, or Fast Frequency Reserve, was introduced in 2020 as a static frequency stabilizing resource to ensure that frequency dips in low inertia situations would not be too severe. It's a short durational injection of active power for 5 or 30 seconds, illustrated in this schematic on the right. And this range, especially the 5-second range, was deemed a suitable region for supercapacitors to deliver this active power injection. Hydropower has historically dominated the frequency regulation markets in the Nordics, but as new requirements were introduced in 2023, it has become more difficult for hydropower units, and especially Kaplan turbine units such as Sollefteå Forsen, to qualify for the provision of frequency containment reserves or frequency regulation reserves. The initial overarching research question was for the combination of hydropower and energy storage was formulated as, can an energy storage system designed for FFR delivery complement a hydropower unit to deliver a wider array of regulatory power? So some background on frequency regulation. For the ones not too familiar with it, I will draw the basics using an analogy of the scale here on the right. So the AC frequency in the power system in Europe is set to 50 Hertz, and the frequency is kept at 50 Hertz by balancing production and consumption at all times in this synchronous area. If production becomes larger than the consumption, the scale tips to the right, and we have an over-frequency situation. And analogous, if consumption is larger or we have a fallout of a production unit, the scale tips in the other direction. So you can imagine a production unit trip by a large power plant, decreasing the inflow of power, causing a dip in frequency, which might be a severe dip if not mitigated. The transmission system operator, Svenska Kraftnät in Sweden, procures capacity of frequency regulation on different markets, and when you're procured, you're reimbursed to always be ready to support the grid frequency in different situations. So this scale was one of the first illustrations I created when I started this project, and I've tried to illustrate one of the truths of frequency stability, which is that of the inertia in the power system, such as large generators rotating have a damping effect on frequency fluctuations as they contribute with inertia to the system. And as we are going, which is illustrated by the blue base of the scale here. So if you have more inertia in the system, the scale is a little bit more resistant to disturbances. As we're going from a system dominated by large generators to a system of increasingly shared distributed production connected to the grid through power electronics, a lot of this inertia is lost, which is represented by the yellow base of the scale. So in a low inertia system, you have to be more active and you have to be more rapid with your balancing resources. As a note, there are several measures that can be taken that allow power electronics to deliver inertia or inertia-like services. I'm sure Massimo has one or two things to say about that. But we're going to focus on regular frequency regulation and the market-based products. So the frequency containment reserves, usually referred to as primary frequency regulation, are split up into 3 markets in the Nordic synchronous area. You have FCRN. N stands for normal operation, with the goal of maintaining the frequency within the normal operational bandwidth between 49.9 and 50.1 hertz. And that's illustrated in this figure here on the left as the lightly blue shaded region. So the frequency is usually within the normal band. FCRD, D stands for disturbance, is activated when the frequency drifts outside the normal bandwidth. The FCRD resources have stricter requirements on activation times to quickly act on frequency deviations if there is a larger disturbance of the frequency. You can see that for this frequency data, 2 days in the summer of 2022, we had 1, 2, 3, 4, 5, 6 cases when the frequency went outside of the normal operating band. In this figure, I've also illustrated the FFR trigger points. So if we would have a larger frequency dip that would go below 49.7 or 49.6 or 49.5, FFR would trigger if we have a low inertia system and inject that active power pulse that I presented in the previous figure. So you can see that there are some different aspects of different frequency regulation services. If you are procured to deliver FCRN, you have to be ready to always be there and move along with the frequency. If you're procured to deliver FCRD, then you have to be ready for a few instants once a day or something to deliver a rapid injection of active power. The content of the thesis is that we're going to discuss hydropower and energy storage combination for a little bit. Then we're going to talk about technology selection, both selection of energy storage technology and converter topology. We're going to go into the design process of a converter design process that we've been conducting here at Mid Sweden, and talk a little bit about submodule prototype construction. But we'll start by going through some of the results from paper 3, since these findings, in some extent, are input to the energy storage dimensioning and design process. And this was a literature review. It was conducted 29 works relating to the combination of hydropower and energy storage were reviewed, and 19 presented quantitative results from the combination, the results of which is presented here in the figure on the right. The y-axis represents the ratio between nominal power of the energy storage system compared to that of the hydropower unit to be hybridized. So the larger the number, the larger the energy storage system in relationship to the hydropower plant it is. The works were sorted into objectives for hybridization because you can hybridize a hydropower unit for different objectives. So I tried doing a categorization. I'll go through them from left to right. The first one is qualification for primary frequency regulation requirements in the Nordics. It's a very relevant resource. The second one is improving black start capability, an in-depth stability analysis of the combination of hydropower and energy storage. The fourth one is FFR, which may enhance a hydropower unit to deliver FCRD, which is our own work. A lot of the works reviewed discussed employing a energy storage to reduce wear in the hydropower unit, which is can be related to the delivery of the FCRN resource, which I mentioned earlier. which is almost always regulating. So when combining a hydropower with energy storage for this application, you can also reduce the wear and tear. There's a large overlap between the two categories, wear and augmented PFR. The augmented PFR delivery is motivated either through the fact that the delivery of primary frequency regulation was either increased in capacity or improved in certain aspects. It is a little bit ambiguous term, but hydro peaking is the odd one out. The large, almost to the right there, which is the primary objective rather focuses on mitigating hours of peak production from the hydropower unit, as peaks in hydropower production may cause damage to river ecosystems. And a large energy storage system was investigated to be combined with a hydropower to remove these peaks but maintain the same power production profile. And the last category, labeled industry, is the result from a market survey on the Nordics on investments on hardware on site by different actors. As you can see, there is quite a large spread between the results. From academia, we span from between 1.5% of the nominal power of the hydropower unit to around 15%. But the spread from the industrial investment is a lot larger and is not as transparent to understand why the different market actors has done why they did. There are probably many different strategies employed by these actors investing in these projects. While academia has a tendency to optimize energy storage according to a set of parameters, industrial actors might have other reasons to maximize their investment. Some industrial actors, however, apparently have tried to minimize their capital expenditure by decreasing the size of the energy storage system in comparison with a hydropower unit. Another important aspect of this review is that we looked at the ratio between energy and power of the suggested systems in the reviewed works. So when working with energy storage systems, you normally refer to the relationship between energy and power as the C rate of the energy storage system. If the energy storage is able to supply nominal power for 1 hour, the C rate is classified as 1. If it's able to support 2 hours of nominal power, the C rate is 0.5. Higher C rates mean higher power to energy ratio. And this, as an example here, the system that we suggested to be dimensioned for the 5-second FFR delivery has a C rate of almost 400 here. One other resource suggested an energy storage of a higher C rate, and that was dimensioned for black start. This was also comprised of supercapacitors. The systems here in the inset with the C rate of up to 4 is a normal operating region for lithium-ion batteries. But when we start approaching 100 and above, systems should be able to discharge at around 30 seconds. So one conclusion from this review is that it strengthens the initial hypothesis that very power-dense systems with low energy content is suitable for the pre-qualification for other FCR products. However, a lot boils down to the individual plant characteristics and what aspects of the delivery that must be supported. So what's suitable for supercapacitors in this picture? I would say the ones that are suited straight off the bat are the 4 highest bar plots here. So when you have a C rate of above 200, then that's a good range. When you start going a little bit below 100, then you're approaching levels where some kind of hybrid might be of interest. So now we're going to take a step down in the level of detail. We're going to look on converter design and the system design that we are proposing. We are suggesting using supercapacitors as the energy storage technology. To inject AC power to the grid, we need an inverter system to invert the DC voltage to AC voltage. Usually we also need a step-up transformer to connect to medium voltage levels, such as 10 plus kilovolts. And the inverter and the transformer are cost drivers for the whole energy storage system package. So we were interested in designing a multi-level inverter system with a low overhead cost per additional submodule, and to be able to use low voltage components to block the voltage in each submodule. We conducted a simulation study, which is the paper 1, to investigate the cascaded H-bridge topology, to integrate the energy storage components as strings of series and or parallel connected supercapacitors in each submodule, denoted NP and NS. So here's the supercapacitor stack in each submodule, and the converter consists of several submodules connected in series in each phase leg. The study investigated the cost and efficiency of the inverter when varying the number of submodules, configuration of supercapacitors, how many switches were needed in parallel to ensure that the converter could deliver the desired power, sustained for 5 seconds nominal power delivery. And a multi-level inverter uses many voltage levels. Each of these submodules can output a neutral or a positive or a negative DC voltage from each submodule. And then when you combine these, you're able to construct the sinusoidal voltage outputs, something like this, utilizing a nearest level control scheme, or something like this if you'd utilize a phase opposition pulse width modulation scheme. But why multi-level and why cascaded H-bridge? So cascaded H-bridge is a complicated topology compared to what's normally used in these applications. For these voltage levels, normally we have something like this, a stack of energy storage components, a film capacitor to maintain the voltage and to limit the ripple on the energy storage component. Here you have a filter and a step-up transformer to increase the voltage to medium voltage levels. And this is a three-phase 2-level inverter. One-phase sinusoidal voltage is constructed through PWM in the following manner, for example. Positive and negative polarity voltage is switched at a high rate. The mean value of the red line, presented in this figure, becomes a sinusoid. And the current injected to the grid looks quite sinusoidal after being passed through a filter. But yes, we were interested in exploring the benefits of the multi-level inverter topology. The fact that we could use low voltage components when switching is one aspect, instead of blocking the whole series connected voltages in the case above. Another aspect relates to the inherent voltage drop from the supercapacitors as they discharge. So the voltage relates to the state of charge as an inverse characteristic. As the state of charge of a supercapacitor depletes, the voltage also depletes. So to be able to maintain a working voltage here for the switches, a DC-DC inverter is employed to ensure that the voltage output to the switching bridge is kept constant. The DC-DC inverter, however, increases costs and reduce efficiency of the system. There are many examples in literature where DC-DC inverters are included in a multi-level inverter, such as the cascaded H-bridge as well. The DC-DC inverter step maintains a constant output voltage from each submodule. The DC-DC inverter shields the energy storage components from certain ripple as well. But we were interested in reducing costs, so reducing overhead per submodule, increasing efficiency, and we wanted to explore removing the DC-DC inverter step. So then we need to deal with this variable voltage, which was done in the following manner. Yeah, so this is the submodule that we propose, very simple stripped down submodule, which has to be, then we have to deal with the variable voltage through, for example, modulation schemes of the inverter. So as the supercapacitors discharge, the operating voltage of each submodule decrease. We use a dimensioning method for the number of submodules such that the desired output voltage can be supplied by a fraction of the submodules when they are fully charged. And we refer to the ratio of the submodules connected in series to supply the operating voltage as the modulation index. So in the figure here on the right, we can see an example of submodules connected in series at the modulation index of 0.5. And 50% of the submodules are connected in series to supply the rated voltage, or the voltage we want to inject to the grid. As the supercapacitors discharge, a higher number of submodules must be connected to construct the voltage waveform, increasing the modulation index to 0.75. And in this example, we can see some results from simulations delivering the FFR pulse of 5 seconds, where as the energy stored in the submodules goes down, the modulation index increase, and if we, to be able to meet the voltage requirements for the grid. Let's go back to some results from paper 1. I'd like to include one slide here where we did an evaluation between the activation requirement for FCRD and along with the activation time of a Kaplan turbine, which is not Sollefteå-Forsen in this case. So the difference between the requirement and the activation time for the Kaplan turbine is plotted here on the right. This is the integration of this area. And compared to the FFR response of 5 megawatts that we proposed in this simulation study, we could meet the energy requirement for the FCRD activation time requirement. So this was used to motivate that the energy storage system designed for FFR is able to support activation requirement for FCRD for this Kaplan turbine. However, it's obvious after been working with this for a while that Kaplan turbines are very different and individuals, and it depends a lot on local conditions. So it's not really generalizable per se. But simulations were performed. Energy content, so the key takeaways are that energy content to meet activation requirement for FCRD were met with the storage designed for FFR. The largest loss factor in the inverter arose from the internal resistance of the energy storage due to the high currents. The cost of the components were deemed competitive for the system. The price of the energy storage was the variable with the most significance. Using a supercapacitor with a higher cost, but improved electrical performance drove the capital expenditure of the system. It would, however, probably drop the operational expenditure. So we only did the CapEx comparison here and did not include operational cost of the system. Okay, let's continue to paper 2. As we mentioned previously, some findings from literature suggested that removing the DC-DC converter interface between the energy storage component and the switching devices here may expose the energy storage to increased ripple and also the switches. So we wanted to simulate and understand this effect, where our hypothesis was that the equivalent series inductance of the supercapacitor, which is quite large in the range of 0.5 millihenry, had a large effect. So the supercapacitor is denoted by this voltage source. We have an equivalent series resistance, which drives losses at high currents, and this inductance, which stores energy as current flows. So when the energy is stored in an inductor through the magnetic field induced by the current, this energy has to go somewhere when the current stops. This is usually called commutating current, and it happens every time we switch polarity or disconnect the submodule. If the current cannot dissipate in an absorption circuit, it induces a voltage spike, which can damage the switching devices and energy storage components here. So we did an iterative design of different absorption circuits in LT-SPICE to understand what the effects of the equivalent series inductance was. So without any absorption circuit, working at 400 amps current levels, which is considered reasonable for the supercapacitor. We got very high overvoltage peaks on the energy storage component, both here, the energy storage component, and the switches exposed to the commutating current. And we're working with low voltage components, so if they are exposed to voltages much above 100 volts, they will break, and we will have a lot of damage. So we need to keep the operating conditions for the switches within their safe operating range. So this overvoltage peak of 2 kilovolts was not acceptable. So we introduce a snubber capacitor, which is a normal step. We get a large reduction in the overvoltage peak, but we get an oscillatory circuit between the capacitor and the inductor. The situation here is a worst case scenario, and this can be damped by including a RC resistance here in the absorption circuit. But we finally went for an RCD snubber configuration, introducing a diode in the absorption circuit to reduce the overvoltage peak even further. So on the right-hand side here, we have enlarged the turn-off instant, so looking at how the overvoltage develops in the circuit. And we can see that current is decreasing from 300 amps to 0 in this case. The overvoltage experienced by the switches and the energy storage components can be summarized as a high frequency and a low frequency component. From the simulation and experiments, we propose that the low frequency component is due to the induced voltage in this equivalent series inductance due to the rapid fall of current. So we will have a high DI/dt in this use case, and that will induce this voltage in the inductance. So it's inherent, but we need to investigate how this affects our system. The high frequency component, this spike here, is due to the commutating current, and this was satisfactorily decreased in the simulation, at least enough to investigate how it would look in a real-life case. So we designed and constructed a submodule prototype. So here we can see the experimental prototype. That was a foundation for paper 2. The control of the switches was done by a Texas Instruments microcontroller. 4 MOSFETs were connected in parallel for each switch to be able to handle as high currents as 800 amps. On the back we have the RCD snubber configuration. In the first version of the PCB we used 3 parallel diodes with ceramic capacitor banks and resistive components to dissipate the energy stored in the ESL. So we evaluated the overvoltage across the MOSFETs using a double pulse test. The double pulse test is a test usually employed to look at switching loss. We can use an inductive load and charge the inductive load with current for varying pulse times to look at different current and voltage levels. So we evaluated the switching transients at the desired current and voltage level, or as much as we could. And this figure presents results from nominal voltage operating conditions. The supercapacitor was fully charged. But while the simulations indicated that overvoltage was reduced to safe operation at 300 amps, the experimental results show that for 150 amps we were close to reaching 100 volt overvoltage. So this is too close to the rated voltage of the switches. So this had to be done something about. Here's a zoomed in version of the previous figure where we can look at the overvoltage peak. So key takeaways from the second paper is that we improved the overvoltage transients, however, not as much as in the simulation study, and higher currents than 150 amps per submodule might yield unsafe operation in this case. And now we're in the additional results not yet published section. We did a second iteration of the submodule design as part of a bachelor thesis. The primary goals of the second iteration was to decrease the parasitic inductance of the switching circuit, to add a RC snubber circuit in close proximity to the switches here to mitigate overvoltages. And the goal of reaching 800 amps per submodule was scaled to 400 amps, and the number of MOSFETs in parallel were reduced to 2 to scale down system costs. And as part of this work, we also increased the detail of our LT-SPICE simulation to better represent the experimental profile of the high-frequency transients. So here we have a simulation of the submodule without the new RC snubber configuration, and a comparison with the RC snubber configuration. So we were hopeful from the simulation once again that we would reduce these overvoltage transients. And experimental results on the second inverter prototype show that yes, we do get a large change in overvoltage as induced on the switches with and without the RC snubber circuit. We can see a noticeable difference on the high frequency overvoltage. So going from, this is working at 0.5 nominal voltage level, so we're approaching 60 volts overvoltage without the RCS number, and we're a little bit above 30 with the RCS number. And for the same operating point as in the ones I showed previously, where we were approaching 85 volts, we're now closer to 60 volts. So we decreased the overvoltage with 40% in this case, which is, I would say it's good. And now we have to explore what current levels can we go to with this submodule. What is the nominal operating point, and what is the safe operational point? So now I'm in the future work part of my presentation, and I'm going to talk a little bit about converter design as it's fresh in everyone's minds. So the second version of the submodule did exhibit a safe switching at 150 amps. Now we need to look at increasing current levels to determine the possible operating point for this prototype. Following this, the project aims to investigate multi-level inverters, not just one submodule. And we need to connect several submodules in series. And then we can start experimenting with different control schemes in the lab as well. Here's a simulation looking at increasing the current levels to above 400 amps. And while this indicates that, yes, we should be able to do this without any issue, we know that simulation and reality is not exactly the same yet. I'm going to talk a little bit about future work on the system design level, looking a bit broader than just one submodule, and also the industrial application. So for the system design, I would say that we need to improve the system design simulations according to a better representation of some physical limitations of the supercapacitors, such as how many supercapacitors can be connected in series for a safe operation, what is the heat development at different current levels for the supercapacitors, because that's one of the drivers for wear. We've done studies where we state that we want to exclude the DC-DC inverter to look at how the system works, but it would be beneficial to also have a simulation study with the DC-DC inverter to have a benchmark operation to compare to. I showed just a very brief slides of nearest level modulation control and pulse width modulation control of the multi-level inverter. We also propose model predictive control in the thesis as one way forward, and a structured evaluation of these control schemes would be suitable. For the industrial application, I would say that we've been discussing the combination with hydropower, but we need to actually propose a suitable dimension for the combination of hydropower and energy storage, and especially for Sollefteå-Forsen. So an improved dimensioning methodology is proposed, or to use a dimensioning methodology already existing in the literature. The same one used for the qualification for the primary frequency regulation criteria that I mentioned from the literature review. And I would also like to lift the perspective a little bit, not only look at the commercial aspects from participating on these different frequency regulation markets, but also to increase the resilience of hydropower units, to be able to do, for example, frequency regulation of an island system, which would be usually even more difficult use case for the hydropower unit. So then there are some other system aspects that we need to respect when working with this kind of operation. And a lot boils down to the control of the hydropower unit and the energy storage unit, because all the dimensioning, converter design boils down to how the energy storage system and the hydropower unit is controlled together, and what services they deliver. So looking more into the combined control of the two systems is definitely part of the future work related to this licentiate thesis. And I think that was what I had to present. And there's some time for questions.
Okay, Viktor, thank you very much for this very nice presentation. I also would like to thank all the audience at YouTube, because this transmission will be closed now. We will continue here in the room and continue in Zoom. After a break of about 10 minutes, so we continue 10 to 2. Okay, thank you very much.